Please find your seat. I'm Erik Aurell from Stockholm. I'm the chairman of the afternoon session. I'm Erik Aurell from Stockholm. I'm the chairman for the afternoon session. It's my pleasure to invite Giuseppe Gonella, who is Gigi on the title slide. Please.
Thank you. Good afternoon. I'm Giuseppe Gonella, and I will summarize in this talk the results of our group on the phase diagram of active Brownian particle. As a first thing, actually, I want to thank the organizers for the opportunity of giving this talk and for the organization of this conference in this mixed way. Okay. And so the summary of this talk is the following. We have already seen some talks today about active matter, so you already had an introduction to the topic. And in this particular seminar, I will focus more on some general features of the phase diagram of active Brownian particles. So there will be some introduction and then some results about the phase diagram of disk and of elongated molecules. And the main line of this talk will be to put these results in connection with what known in melting transition for hard disk, and with what known from the Kosterlitz, Town, Alperin, and Nelson Young theory. So let's go to a very quick introduction. So active matter, as we have already listened, is out of equilibrium matter. We can see this in this way, out of equilibrium matter, with some external or some driving, which depends on the local states of particles. So in this sense, is a bit different from other kind of driven non-equilibrium matter. As we have seen in the talks, for example, by Volpe, by Giovanni, we can have active matter on very different scales, and they share some common features. But what I'm going to describe is mostly related to self-propelled colloids, so at least it can be used to describe the experimental behavior of bacteria or self-propelled colloids. So let's start from some very general observations. I said that I want to put in contact the behavior of hard disk with the behavior of active particles. So first of all, let's give a look to a simulation of standard hard disk, just interacting by a repulsive, very short range repulsive interaction. So they are hard disk, and this is there is a tracer particle, the yellow one, and this is the kind of motion that one can observe at a relatively low density. Sorry, maybe you don't. It's okay. Yeah. And on what we want to consider in this talk is an active version of this system already introduced today, not so different from the active Ornstein-Uhlenbeck particles with interaction seen in the morning. But in the morning, we only consider this in some seminar, single particle behavior. So the particle that we have in mind are disks like this that have also another degree of freedom, which is a polarization. This polarization evolves in some way, for example, by diffusive rotative behavior. And the new fact is that that affects the equation of motion of the disk. We will see later explicitly the equation of motion, but let me first show the picture. So there is a force acting on the disk along this polarization axis. That is another, as I said, another degree of freedom of the particle. And these kind of active disks are realized in many different ways, and this is a quite known experimental realization made by Buttinoni et al., the group of Leeuwen in Germany, I think. And here they move by thermophoresis. There are other mechanisms that produce this force. These are colloids with half of the colloids coated by carbon, and then when there is a laser light acting on the colloid, there is some heat that produces some flow around the disk, that pushes the disk along each red arrow. So I will come later to the full meaning of this picture, but let's give a look to what happens to the same simulation when I put in the equation of motion also the force coming from this polarization. What happens is that the standard Brownian motion seen before becomes a sort of persistent Brownian motion. We have straight pieces of trajectories more persisting in the same direction, and this is an example that we can see. So diffusive property change, and we can study a lot of properties at low density. But the most interesting facts comes when one considers what happens with this persistent motion of Brownian particle at higher density. So here, let's come back to the same picture as before. And the meaning of this picture is the following. This is taken by the physical regulators, by the German group. Imagine that you have three colloids all pointing in the same direction. So you see that if the particles all go in the same direction, they tend to become stuck at certain points. Of course, there are also thermal fluctuations due to the Brownian motion, to the thermal noise that change the position, and also there is the diffusive motion of the polarization too. But if the density of these active colloids is high enough, what happens is that you observe the formation of clusters of these particles. And this is a very much studied, quite understood fact that is called the mobility-induced phase separation. So these active colloids, even in absence of any attractive force, they make a phase separation between a low density phase and a phase done by high density clusters. So this is an example of simulation. Oh, sorry. Oh, sorry. Stopping the movie. Oh, okay. And these are are molecules, but for what I'm going to say is the same. So, I don't know, there is some problem in the movie. And you see that there are clusters of particles that are forming. And if this movie would have continued, you should have seen a more complete. Okay, so phase separation. In the particular case of this movie, since these are molecules they are dumbbells actually, they combine each other in a way that the cluster also rotates. And this is something more observed experimentally, but I don't want to discuss this now. So this is what comes from simulation, and what was quite known also before we considered these problems. So the question that we considered with the friends and colleagues, Letizia, Cugliandolo, Ignacio, Pagono Barraga, Damian Levis, and the other students in Bari, is what happens? Sorry, the question that we considered was to make a connection with what happens in passive standard disk, where also the melting transition occurs at high density. I have to say that this mobility-induced phase separation is also observed at density quite low. When I say density, I mean parking fraction of the system, and you observe phase separation for standard active force also at packing fraction of the order of 0.2, 0.3, 0.4, depends on the parameter of the system. While melting of hard disk is observed at 0.7, and we will see better now which are the number. But what was completely missed in the studies on this problem was the relation with standard transition of hard disk, which is something also quite obvious to consider. One can think to consider a standard hard disk system and switch on the active force and see what happens. And this is what this has been done less in literature. So this was our starting point, and maybe I need to summarize some very known and a bit old results on melting transition in the two-dimensional system. So this was already known a bit. So some of these points were known by the work of Landau, Mermin and Wanger's theorem, and other problems, the fact that you cannot have a proper order in two dimensions and all these things here. But who proposed the realistic scenario for transition in two-dimensional system were Alperin and Nelson and also Young, following by applying the Kosterlitz-Thouless theory for topological transition. Following this classical scenario that you can find on book, at very high density, if you consider disk particles in two dimensions at very high density, you expect to have a solid with positional order, but without orientational order. And then if you decrease a bit the density, you have a liquid crystal system with only orientational order, and where the positional order is completely lost. To lost completely, I mean, without no positional order means that if you calculate correlation function related to position of particle, they decay exponentially. While long range means to have power law, quasi-long range means to have power law correlation function for the proper order parameter that you are going to consider. And then, if you decrease a bit more the density, you go in a disordered system. So this scenario that I put here actually has been studied a lot, considered a lot in simulation and of many kinds, of Monte Carlo, molecular dynamics, because it was not easy to find this numerically at the beginning. Only in very recent years was the group, especially the group, a French-German group by Bernard and Kraut. This is a French group, actually, that clarified the following fact, that actually the first transition between the solid and the exotic phase was actually a Kosterlitz-Thouless transition, while from the exotic to the liquid, what you find in simulation is, was a coexistence region between exotic phase with higher density and liquid phase with a lower density. Here, one of the reasons for the fact that this transition has been found not easily is that the density interval between the coexistence density is very low, and you need very massive and accurate simulations for finding these results. In this picture, you find on the left a visualization of the exotic order parameter on the boundary of the coexistence line of between exotic and the liquid region. So everything red means that you have everywhere orientational order. If you have many colors like here, means that the system is disordered. On the other column, you have a contour plot of the density, and if you look carefully, you can see that exotic ordered phase correspond to a bit higher density. And those ones are our simulation that confirm results by previous groups. So the standard theory now, the standard point for the phase behavior, phase diagram of hard disk in 2 dimensions actually is this one. Now, almost everyone believes in this picture that there is a Kosterlitz-Thouless transition, I repeat, from solid to exotic, and the first order transition towards the liquid case. So our point was to put these facts in the context of active particles. And now this is the model that I said before that we consider. This is a model originally introduced by Fili and Marchetti for describing these active colloids, of which we saw before a realization. And I is just the index for each particle. So for each particle, we simulate a overdamped Langevin equation. Well, all this bit is complicated to read, but it's just excluded volume interaction introduced by a very stiff potential. We use the not Lennard-Jones, but we use only the repulsive part of the Lennard-Jones, but with a very high power, 664 repulsive the power. And we did the same as other groups. And then there is the standard thermal noise, this one, white noise. It's this one. And then in the equation of motion, the new fact with respect to standard Brownian motion with the excluded volume interaction is the presence of this active force whose strength is constant with a direction Ni that depends on an angle that changes in a diffusive way, in a standard way. So this is in a sort, in some sense, the standard model for these active Brownian particles with respect to the Ornstein-Uhlenbeck version of the model. This has been studied more or less they share the same features. Actually, that one is more easy. The Ornstein-Uhlenbeck can be analytically studied at low density in a better way. So the parameters that we have in this model and that we are in simulation basically are 2, is the density, the number of the particles that we consider in a fixed size of the system, and the intensity of the active force, a fact that actually we use through some number that is called Peclet, active Peclet number. So when in the following I show Peclet, that you can think to that like the intensity of this driving F active force. And so this is the model for active Brownian particle. And this is the main results of our simulation. I will first show you the phase diagram and then some comment about this. And so basically what was known before our work mainly was just this part here. So the part on mobility-induced phase separation, where you see at the density 0.1, you already see a Peclet 100 separation between low dilute phase and domains. Let me tell you, just for having some idea about this number, that the Peclet number evaluated for bacteria is of the order of few hundreds, could be 300s, 400s, 100, depends on the case. And maybe for self-propelled colloids a bit less, but of the order of the hundreds. And what we did so was to study the other part. You see that at Peclet 0, this is an enlargement in the inset of what happens. At Peclet 0, we have the solid. Then we have a very teeny region of exotic. Then we have coexistence between liquid and exotic, and then liquid, that means disordered. So our results show that actually when you increase the Peclet number, this exotic region becomes larger for a while, and the coexistent at a certain point disappears. So the coexistence region ends in a critical line. A critical line that I anticipated, there is no time to show everything, but in the critical line our indication is that a critical Kosterlitz-Thouless line. So when you increase activity, you go from this coexistent to a standard, more standard scenario first, between where you have solid, exotic, and liquid. And then, at the end, you arrive in the MIPS region. And that is here, where there is another coexistence line between high and low density. Look here, so here in this region, the phase separation here is of liquid gas type, actually, because you have on the boundaries, for example, Peclet about 100, a bit less, you have no exotic order, but you have the boundaries. I mean, what coexist are two not exactly ordered phase at higher and lower density. So this is the main results of one of our paper. And this result is based on the study of the pressure that I don't want to comment too much now. And you see that at small Peclet, you have an horizontal regime in the pressure, P against the density. And this horizontal behavior of the pressure becomes shorter when you increase Peclet from 0 to 3 and then disappears. And then again, when Peclet is quite high, like in the bottom left picture here, again, you have an horizontal part in the behavior of the pressure that corresponds to the MIPS. And then, okay. And the other important ingredient that we used in our simulation was the behavior of the correlation function. For example, let's comment just on the right picture here. So you see that this is the behavior at, I think, Peclet 10. Yes, it is written there. And you see that the yellow curves are in the solid phase, and then at a certain point they change behavior and they decay very fast when you go in the exotic phase. This is the translational correlation function. And similar things can be found for the other correlation function describing the exotic liquid transition. Something more new that I want to show here. There is no time to describe all this story, but these topological transitions are related of two different kind of defects, unbinding transition. So the solid exotic is related to the unbinding of this location, the exotic liquid to the unbinding of disclination transition. All let me give other 2 or 3 minutes, not more. Yeah. So let me tell you that the Kosterlitz-Thouless-Alperen-Nelson-Young transition refers to these local defects. But actually, in simulation, you find many more extended defects, cluster of defects that actually in the exotic phase are the dominant ones. And as you can see from our paper, from the statistic of what we found, and what we found is that there is a percolation transition of the defects that occurs very close to the liquid exotic transition. Actually, here there was a big problem. Let me just mention this problem. If is the percolation transition that distinguishes between critical or first order liquid exotic transition. This was a big problem in soft matter theory, but what we problem of disks, and we found that actually in both cases we found the percolation of defects, and this is another part of our job, and this is the finite size analysis that we did for studying this percolation. I don't want to mention this, but let me just give a look to this picture, because we studied also dumbbells. In dumbbells, these dumbbells are self-propelled along their main axis, so, and then the rest is more or less similar to the disks, but they have some non-symmetric geometry. And since they have not a convex shape, they become aggregated more easily because they can become jammed together. And we have studied also the phase diagram of dumbbells in the same way. And here there is a different feature with respect to the disk, in the sense that there is no interruption from the coexistence region at low Peclet, or corresponding to the passive limit, to the one that corresponds to the mobility-induced phase separation. And this has been considered something not expected in the literature of these things, because everyone considers only the mobility-induced phase separation region, while, for example, in the case of dumbbells, actually we see that is actually the coexistence region at small Peclet that then extends and becomes larger when you increase the activity. And then there are some of our results, there is no mention of percolation that we consider also an important point. And thank you very much.
We thank the speaker. We have a few minutes into the next talk. May I ask the technically responsible to bring on the next speaker, who is an online speaker? Yes, please. Do you want to speak in the phone?
So, Beppe, what does control the width of the blue region? So do you have a way of engineering that in such a way to make that phase larger?
The width of the blue region. In this diagram, actually, it's just density per class. So your question is, what other parameter we can change for changing that?
To change the structure a bit.
Actually,
to improve,
just by chance,
to promote
actually, what we found is that when inertial effects are important, the ecstatic region becomes larger, for example. Okay. So when you go from overdamped to underdamped motion, what we've found is that the region, the critical line does not go towards the high part of the phase diagram.
I was asking because it's really a thin
at the beginning,
strip,
okay. No, at Peclet zero, I cannot answer you, because if you change the potential, let me tell you, this French group has done a lot of different kind of simulation, but that region always it is very teeny. You can change the potential, but if you change the potential, what changes the coexistence region, not the width of the ecstatic.
I guess we can have time for a very short, very short question, if there is one. Otherwise, we have to move on to the next speaker. There's no short question.
Grazie, Eric.
Okay, so we move on to the next speaker. We move on to the next speaker, who is David Dean, who will join us over Zoom.
Yeah, can you hear
me? Go there. I will stand up so that you can see me somewhere in the middle when you have 5 minutes left. You should have 25 minutes for the talk and 5 minutes for questions. You can have less for the talk also if you like.
Okay,
please go ahead.
Put my timer on. Well, thank you for inviting me. It's a real shame that I couldn't be there, because I see the weather in Trieste is absolutely fantastic and it's absolutely awful here in Bordeaux. So I'm going to talk about a nice little problem that's related vaguely to active particles and generalizes some of the questions that people ask about general active type stochastic processes. So this work was done with Satya Majumdar, who's at the University of Paris-Saclay, or SAY, as we used to know it, and Shaw, who's in Sergi Pontoise University. And so it was interesting. So this was really a sort of COVID collaboration. We started talking about this problem, especially me and Satya, by Zoom, while he was stranded at in Bangalore, and he couldn't get a flight back to France. So he had this problem that was on his mind, and the other problem was he was running out of beer and cigarettes because of the lockdown there. So anyway, this was a sort of, this was an interesting Zoom collaboration. So actually let me just explain the basic problem. The basic problem is, imagine just take this diffusion equation here. So I'm going to have n derivatives. So I look at a generalization of an acceleration, and I'm just going to drive the process by white noise. So this is a well-studied problem. So you imagine white noise is the sort of classic passive thermal noise. And if you look at this process, if I just have n equals 1 here, then if I integrate the equation, if I integrate white noise, I just get standard Brownian motion, okay? And what I'm going to do is I look at this class of processes, I'm going to assume that everything starts off at 0. So all the derivatives, the initial position, the first derivative, up to the n-1th derivative, I'm going to set to 0. And so you imagine if I integrate this equation, if n is equal to 2, then that's what is known as the random acceleration process. But the formal solution is the integral of a Brownian motion. So you're looking at the area under a Brownian motion. And so, and obviously you can ask this question about what happens for general n. Now, the interesting thing is that n doesn't necessarily have to be discrete. Okay, you can actually, you know, this solution here was written down by the great Paul Levy in 1953, and it generalizes this general acceleration process driven by a noise to a non-integer n. Now, the thing is, because this is a Gaussian and you're basically integrating a Gaussian, you've got a sum of Gaussian processes, and so everything becomes Gaussian. So if you want to solve this problem for any sort of Gaussian noise, you've completely solved the problem just by if you compute the variance, okay? And then you know that this is what you put in your Gaussian probability distribution function. So if you actually take this representation and you compute the variance, what you actually find is something strange happens. For n is bigger than or equal to 2, everything seems okay, but a half rather. But you can see when n is equal to half, you run into a problem here. You end up with a negative variance. So something is strange is happening to this process, and it's ill-defined for n less than half. So obviously, we'd like to, if we're interested in this, let me see, should I move along? Oh, well, here we go. Now, when I mentioned this n continuous, obviously there's a realization of this. If you imagine you take some sort of elastic model, so this could be a sort of a polymer-Rouse model, or you know, just a model for an elastic interface. So if you look at this energy functional here, you have this energy, this surface energy term here, and imagine I just pull up at the origin with a sort of delta function force. So I just pull here. So I'm just basically pulling the interface at the point x equals 0, okay? So I can imagine this is my driving force. Now, if I just look at the response to this force, because the problem is linear, or if I ignore temperature, if I write down the dynamics for this, the general form of the dynamics is that you have dH by dt. So the general form of overdynamics is that dH by dt is equal to, you have some dynamical operator here, depending on the type of dynamics you want to consider, times the functional derivative of this energy functional with respect to h, and it gives you this equation here. And so actually, if I ignore this force term, I mean, if I take z equal to 0, I find model A, which corresponds to Edwards-Wilkinson, the Edwards-Wilkinson equation. Or if I take z equal 2, then I have some dynamics which conserves the height of my model. So I have a height conserved model. And if you look at, say, model B for 2 separated phases, the effective dynamics there gives you ZD is equal to 1. Okay, so which gives you the t to the 3rd scaling for model B dynamics. So this model, this dynamical exponent can take several different values depending on the model you're looking at. And if you actually just solve this in Fourier space, okay, you just take a Fourier transform and then you come back and look at the position of h0 of t, you find exactly this sort of integral, okay? So this t minus s to this power here is just coming from the fact that you've just integrated over the Fourier modes. And obviously it depends on the dimension of the space. See, it's up here, and the dynamical exponent. So actually, if you look at the sort of Edwards-Wilkinson model, the Rouse polymer, that corresponds to n equals a half, and the conserved model would correspond to n equal to a quarter. And this is for d equals 1. Okay, so you can realize these strange integral forms. Okay, now let's ask what happens now if the noise is colored. Okay, so the noise, so let me just, for the moment, I'm just going to talk about the variance. Okay, I'll come back to the full distribution later. But if I take this commonly used, so this is this correlation function is a correlation function for lots of different things. Okay, so it just decays exponentially. This can be generated, you know, from an Ornstein-Uhlenbeck process, or we're going to see that it can be generated by a telegraphic noise. That's what I'll come back to. So actually, if you actually look at this integral here, rather surprisingly, normally you can only do asymptotic analysis, but if you tease Mathematica enough and help it with the integral, you actually find that this variance, x squared of t, is actually given by a formula, an explicit formula for all times. Okay, normally when we look at these sorts of formulas for sort of persistent random walks, we do the small t and large t expansions. And so at small times, what you basically find is that v of t, you get this t to the 2n. So remember, Andrea was talking about ballistic motion. So this is the equivalent of the ballistic motion regime. This is basically related to the fact that the particle hasn't yet flipped its spin. And if you look at large times, what happens is that for n is bigger than a half, it grows like t to the power 2n minus 1, the variance. For n equals a half exactly, you actually find that it grows like a log, and there's this constant phi 0 that you can compute as well. And so it's growing very, very slowly at this critical point, n equals a half. And then for n between 0 and 1, you enter into a localized phase, and you can actually show the late time asymptotics is given by this formula here. Okay, so as in usual with all relaxation times, this behavior is valid for t less than 1 over gamma, and the long time behavior is valid for t greater than 1 over gamma. So actually, so you basically, what we can say is that we've solved this problem, therefore, for an Ornstein-Uhlenbeck process in equilibrium. And the Ornstein-Uhlenbeck process in equilibrium, suitably rescaled, has exactly this correlation function. So we've solved the problem. But now let's look at the other problem. Let's try and look at, so this is the problem I'm talking about. If I look at this process here, d sigma by dt equals minus gamma sigma, and I have this white noise here, this gives me the Gaussian, this is still Gaussian. This is what we call the Ornstein-Uhlenbeck process. But let's have a look at this other process here. Let's take an equilibrated telegraphic noise. Now, this is a model that's used for a simple model for run and tumble bacteria in one dimension. You can think of the state where it's +1 as it's basically moving forward in space, moving to the right, and then it can flip and it will go to the left. And so we're going to look at a system where it changes between these two states at a continuous time rate gamma. Okay, so I wait, with the probability gamma times dt, I change the sign. So the steady state of that is obviously the probability you're going to the left is equal to the probability of the right is equal to a half. And so actually a number of authors have looked at this, and you can actually compute the full probability distribution for this n equals 1 run and tumble model for a bacterium. And so you find that the interesting thing about this thing here is that you have a sort of light cone structure, because obviously if you look at these last two terms here with the delta functions, this basically corresponds to a particle that started moving off to the right with a positive velocity, and exponential minus gamma t is just the probability that it's never flipped. This is the corresponding term for a particle which started going to the left, okay? So, and this variable rho here, you see it's a light cone-like variable as well. It's, it's exactly the sort of v squared t squared minus x squared. So it's normal, okay, that this process has a finite velocity. So unlike the diffusion equation, the probability that it moves quicker than its maximal speed, which is v0, is 0. Okay, so it's a process which cannot go off to infinity at finite times. Okay. So actually you can look at this just to check things out. You can actually simulate the variance. So this process is very easy to simulate, because basically, well, you need a good simulator to do it. And basically what you do is you just integrate the equation in terms of the flipping times, and you find this formula here. So basically the whole process can be generated by just producing a sequence of these flipping times. And you can see here, for n equals 2, you have the increase of the diffusion of the variance, it's growing. Here we have the slow logarithmic growth, and here for n equals a quarter, which is obviously less than a half, you have the saturation to a finite value. Okay, now the interesting thing is we start looking at the PDF. Obviously, these simulations of the variance, they should behave in the same way as colored OU noise. Okay, now let's have a look at what happens when we look at the distribution. So these simulations are done at time t equals 5, starting from a symmetric initial condition. Okay, so what you see, so basically you're evolving two delta functions at the origin in terms of the velocity, of each with a probability of half. And you can see here in this simulation that we have the variance, which is growing like t to the n minus a half. But you can see this is the extreme. These are the particles that really haven't flipped a lot, okay? And they're growing like t to the power n. If you go to n equals a half, you see the structure is changing slightly here. So this region here will be growing very slowly, and this region here will actually be saturated. This region here will be going like t to the half, but this region here will be growing logarithmically. And here we go to n to the quarter, and basically what happens is that this region here continues to grow with t, but here the scaling is different. So there's a real difference between n bigger than a half and n less than a half. But actually, there are lots of strange things happening in n, which I'll come on to. Okay, so this atomic measure just comes from this fact that these are just particles that are never flipped. So if I say the x star of t, you can easily show this is the maximal velocity, v0 t to the n over gamma n plus 1, just integrating the equation directly. And so you find these peaks are just coming from this term here. This is the atomic part of this. And of course, they decay to 0 very quickly as time becomes long. Okay, so actually it looks like quite a difficult process, because actually you have, in principle, you have, all the derivatives. So in order to analyze the process, you need to know what the dx by dt is, and all the other, the lower moments. This is what the lower derivatives. This is what makes something like the random acceleration problem very difficult to handle. So remember, this is the formula. Actually, if I just make a change of variables, s goes to t minus s. So this doesn't look as if it's done me any good. It's just changed the t minus s here to s, and the s here to t minus s. But actually, the thing is, if I look at this process, sigma of t minus s, this is just like the process started at t, run backwards in time. And because I'm taking sigma to be in equilibrium, actually that has the same process as that has the same statistics as a process which is run forward in time. Okay, so this is something which only holds for the statistics at a single time. And the way of seeing that is, if you want, you can basically look at the moment generating function. So the Laplace transform of the PDF, it's given by this. And what you can show is, if you basically compute the moments of x of t and x tilde of t, when you use time translational invariance and time inversion symmetry, basically you find all the correlation functions turn out to be the same. So you can actually look at this process here. And while you couldn't take the derivative of this process here, you can take the derivative of this process here, and you find a really simple process. So basically this equivalent process, which is statistically in law, is statistically identical in law at the single time, basically obeys this equation here. So this is why you can actually analyze this problem. So the key to analyzing the problem is to do a Feynman-Katz analysis. Actually, there are a number of different ways of solving this problem. I'm going to show you the first way that we did it and the way that we published. So let me look at this generating function. So I'm just looking at this expectation value over this expectation value over all the paths which finish with sigma t equal to plus or minus 1. Okay. So I don't know if, Feynman-Katz sounds very complicated, but it's very easy to see what happens. All you do is you work out what happens when I go to t plus delta t. Well, the thing is, if sigma doesn't flip, which it doesn't flip with 1 minus gamma delta t, you have all of this exponential with its integral up to the time 0 and t, and you just pick a little bit more between t and t plus delta t, but with sigma equal to 1. Okay, so basically you get a term like this. So that's sort of the gain term, or there's a sort of the loss term, if you will, and this is the gain term. So basically this is just saying that gamma, the process flips, and you end up going to the state with a minus sign, which you do with gamma delta t. Obviously, you've moved a little bit, so the integral is changed, but the order in which that integral is changed is of order delta t, so that gives you a delta t squared term. So actually, I do exactly the same trick for the process, for the function u minus, and you end up getting these two equations here. Now, if I look at equilibrium initial conditions, so if I set t equal to 0, well, there's nothing here, so this term is equal to 1. And this is just, the expectation value of this is just a half, because you're equal to 1 or minus 1 with equal probability. So there you have your boundary conditions. So now actually it looks like a very simple problem. So you have lots of different ways of doing it, but a nice way of doing it is just to look at the sum of these two processes. So this is basically just removing the conditioning on the final point, because you're adding two delta functions which are equal to 1. And this is another term where you're looking at the difference between these two functions. Okay, so if you use that, you find there's a very simple equation for un of t, and there's a very simple equation for wn of t. Okay, and the additional conditions are clearly, so this is, I mean, this turns out to be quite subtle. U is equal to 1, un is equal to 1, and w is equal to 0. So now what you can do is, obviously un is the sum of u plus and u minus, so it's just the Laplace transform of the probability distribution that we're interested in. Okay, and so now what you have to be slightly careful with the initial conditions in this, because it looks as if du by dt should be 0 because it was proportional to w, and w is 0. But the problem is, you see that for n less than 1, this term here is diverging. So you've actually, you have to be a bit careful. And basically you find that these are the effective initial conditions. You have to integrate the equation for w in order to find the initial conditions correctly. So these are your initial conditions, and you can see that they go, there's a divergence at n equals a half. So you see this business about n equal to half being fundamental in the problem. Now, in order to solve this problem, actually make a large deviation type ansatz, and you're basically saying, if you think about, you can sort of argue this, but you can argue this in a slightly more systematic way. You motivate this. So basically you say, well, actually, if I'm interested in at late times, I'm going to look at the scaling variable x divided by x star of t. So this variable, which I call w later, is basically something which is between 1 and minus 1. Okay. And if I assume this large deviation behavior, and so analyze this form here, you can see that if I put in this large deviation form here, basically making a change of variables, z is x over x star, it becomes this form here. And this is the corresponding variable for w. So this functional, Feynman-Katz functional, is characterized by this function hn of w, which is obtained simply, which is related. So if I go back to the calculation in the terms of z, it's just given by a saddle point. Okay, so basically it means if I can compute this function hn of w, I can invert this Legendre transformation, and I can compute this large deviation function for the probability distribution function. Okay, so now it's things get a bit technical, but the interesting thing is if you insert this ansatz into the equation for un, basically what you find is that, so this function gn is simply related to hn by a first order differential equation. You can go ahead and solve all this, and not going through the details, what you find is this hn of w is given by this form here. Okay, so it's just solve a quadratic equation and integrate this first order differential equation with this quadratic term. So now what you have is you've got this problem of, in order to solve the problem, you need to determine c, and you have to determine the sign of these two square roots, okay? And it actually turns out, you can see that despite the fact when I was looking at the variance, n was equal to a half looked to be important, actually it's n equals 1 here. You can see that n equals 1 is playing an important role, and we have to consider these two cases, n greater than 1 and n less than 1 separately. So in the case n equals 0, actually, we take the limit t goes to infinity. We want to keep this scaling variable w to be finite. Okay, So this means as n because n's bigger than 1, actually, I need to consider the limit where mu is going to 0. So this tells me that hn of w must be going to 0. So hn of w as it goes to 0 actually should be equal to 1, actually. That's a mistake here. And by symmetry, there should be a symmetry. The derivative of the origin should disappear. And actually, using these facts, you manage to find that c is equal to 0, and you have to take the negative root. Okay, so you find this full form for the Legendre transform of the full large deviation function. Now, when n is less than 1, you need to consider the boundary conditions as mu goes to infinity, because actually, if you want to consider the case w of order 1. As n is less than 1, you can see here that mu will have to go to infinity to keep w of order 1. So this changed the analysis. And the interesting thing is that we can no longer use the boundary conditions at w equals 0 to solve the problem. But what we can do is we can look at the large deviation function, what we expect the large deviation function to behave at the edge, where for this process which hasn't flipped, we said, you know, this is just the probability you haven't flipped, and this is the maximal displacement. And this applies for both left and right, so you actually find the large deviation function in this case is equal to 1 minus the modulus of w. You can then solve the differential equation for hn, and you find, oops, what have I done? What am I done? Actually, I've just opened an email from Satya he's just sent me. So let me see, what have I done? Let me just before sharing at a new share, let me just go back to the original. Okay, so I don't know what. So actually, yeah. So excuse me. I don't know what I've done to my. PDF file. It seems to have opened an email that Satya just sent me in my PDF file. Anyway, so actually you can see, I hope you can still see the formula. So you actually find this different form for hn of w. So it changes when you go from n to n less than a half. And you can basically solve everything exactly using, you can plot these solutions using Mathematica. Mathematica has a parametric plot function, so you can see how that can be implemented, which is quite useful. Satya showed me how that worked. And then as you look at the asymptotics, of course, for n is greater than a half, you basically have a region where you see a Gaussian behavior. So this is compatible with the variance. And indeed, when you look at near z equals 1, you can see that for a half, n between a half and 2, you basically find this sort of singular behavior. It goes like 1 minus z to the half. But actually, so you actually find that n equals 2 is also a special point, and you can see that the behavior, this critical exponent as z goes to 1, becomes 1 over n, which matches with the 2 here, of course. And for n less than a half, you basically find that as z goes to 0, you find this no longer Gaussian, this z to the power 1 over n form, and g of n is given by this explicit form here.
You have 5 minutes left, including questions.
Can you still see my screen?
I saw, but you froze for a moment. That's true.
Actually, so I don't know why. So you can only see half of the screen, right? Or can you see the full screen?
Why don't you quit and enter again the presentation?
Yeah, quit and go back again.
Okay,
But you only have 5 minutes.
Let me stop the share. Okay, then I'll do share screen.
That's actually much nicer.
Sorry?
Actually much nicer to see you. It's
Well,
almost
yeah, it's nice to see you as well. Yeah, yeah, all the people I haven't seen for a while. So let me go back. Let me just let me do something here. Let me just try and get back to
You have a good camera.
Yeah, I have a good camera, and I've got a good suntan because I was on holiday in Wales, which is always a good good place to get a good suntan. Okay, let me see if I can get this. let me see, presentations.
Maybe you can just round up in words.
Yeah, okay, so I'm going to round
have
up in words. I'm sorry about that. Okay, let me, I don't know, my computer has just done something very strange. I can no longer get out of, I can no longer get out of this thing. So we're basically shown that, so you look at this very simple run and tumble process, and you generalize it by using this run and tumble noise, this telegraphic noise, as the basis for integrating it up. So you could be looking at the area of these sorts of processes, or we've seen that it can apply to polymers as well, and sort of interface models. And so we're basically seeing, so this model, with respect to the Gaussian model, actually, the region where n is between 0 and 1/2 now it makes some physical sense, and it has completely different behavior at late times to the case where n is greater than 1/2. And there are also a few extra little, there are sort of minor phase transitions and critical exponents happening basically at n equals 1 and n equals 2. So I thank you for listening, and I'm really sorry about, I don't know what I've done.
Okay, we thank the speaker. We're happy anyway.
Yeah, well, I'm sorry. Yes, okay, thanks. So if there's any
technical parts to get the next speaker ready. So it's Joanna Smoluchowska. And I think we have time for one question, I guess. I'll come down with the mic. Yeah, a moment.
Hello, I'm Benjamin. Thank you for the talk.
Hello.
I have a question in how much you can generalize this to fractional driving noise, or if you can just absorb this into a different n.
Yeah, actually, fractional Brownian noise is actually quite a bit different to this, right? I mean, actually, Levy introduced, when you look at the correlation function, actually, when Levy introduced it, actually, one of the criticisms of the Levy model was it gave too much importance to, what happens at early times with the noise. So, I mean, perhaps I don't know. There might be some trick, right, that allows you to do it. But I suppose I suppose if the noise is somehow, well, I guess if things are Gaussian, right, you could probably just go ahead and calculate most things, right? I mean, if you're looking at Gaussian processes, then there shouldn't be any problem.
But it has strange correlations, as far as I remember.
Yeah, it has strange correlations. So, I mean, you'd have to put it into, but in principle, I guess you can, just integrate it up, just the way that, it's exactly the same calculations that I did for the 2-point function, right? But you have a different 2-point function there, so you have to look and see, where this exists, where if the variance exists, or if it diverges.
No, I remember there was some calculation from the integral of Brownian motion when they were to be generalized to the integral of fractional Brownian motion. They were much more difficult. It's kind of my personal scientific past.
Yeah, that's true.
We have to thank the speaker again.
Okay, thank you.
Thank you. Thanks a lot. And I can see Joanna Smoluchowska.
Yes,
Cześć.
correct.
Jak się masz?
Bardzo dobrze. So, should we switch to Polish?
I don't think so. I think it will be a kind of limited audience, but nice to see you after such a long time.
Yes, nice to see you. So, should I share my screen?
Yes, I should present you first. So it is my pleasure to present the third and last speaker of this afternoon session, Joanna Smoluchowska from University of Warsaw. And the floor is yours, please.
Thank you very much, and thank you for invitation. I think my talk will be slightly less technical than the other talks, but I hope it will be still interesting. It will connect the topology with statistical physics and biology. And so let me share the screen. I hope so you can see now my screen. Yes, probably yes. So as I said, I will talk about connection of statistical physics, protein, and topology. So let me just move. Yes, so you know that nodes are very common in our daily life. Nodes probably you can find easy in Trieste when you go for sailing. You use the nodes to park your sailing boat. You can see the nodes in nature, that you can have some tree that can be they can make links, for example. You know that nodes are very common in art, and art is a part of Trieste that you can see in any part of nice old building in Trieste. There are some nodes, what I remember. Nodes are very common in chemistry. They are found in physics, and they exist in biology, in DNA. However, for a very long time, it was believed that nodes cannot exist in proteins. So, for example, in '94, it was suggested that over that time, we know there was 400 protein structure, and some mathematicians analyzed this polymers, and they found out that proteins are not knotted. And one of the reasons was conclusion is that from the statistical point of view, the knots probably the knots cannot be formed on protein, because it will be too difficult for them to fall to the native position. So just to remind you about the proteins, that we can also think about them as polymers. So proteins are made of 20 different amino acids, and they are connecting in linear chain, and this chain has to fold to some unique three-dimensional structure. And this unique three-dimensional structure is the form that we call is native, and it's biologically active. So we usually say that proteins are classified based on the sequence, and then secondary structures, or alpha helix, beta term, and they have the three-dimensional fold. But what I would like to tell you that you also need to take into account that protein can be knotted, because today we know that at least 7% of protein possess topology. And as you can see in the figure on your left side, this is a protein, and probably by visual inspection, it's very hard to see where it's not located. And as you probably know from the mathematics, knots are only properly defined on closed curve. So in this case, you can has two approach. You can just pull the protein by the termini, and you can find out that protein is knotted. Or you can have the more statistical approach. You can extend termini to infinity, then close them on the sphere, and then use the familiar polynomial for you. So you can use the Alexander polynomial or Hoffly polynomial to find type of the nodes. However, protein can also make something what we call lasso. So in this case, you have the protein chain that is closed by one of the stable bridge. We call this the cysteine bridge. And then you can find out that one of the tail is piercing the loop. And moreover, you can find out that some proteins possess something what we call links. So you have one chain that make two stable connection in such a way that two circles are across each other. So because from the statistical point of view, we'll expect that long polymer chain should form knots, and different type of the knots. And in the case of the protein, we know this is only 7% of protein that are knotted. Then you can think why protein do not form knots, or why they are not so, why knots in protein are rare. So the question that I am asking is how to characterize knots or entanglement or non-trivial topology in protein. Additionally, the basic fundamental question on the border of biology and physics is what is the biological role of entanglement? So maybe knots were formed during the evolution, and maybe we will observe more. And as you know, there was the AlphaFold using the artificial intelligence was recently predicted the structure. So maybe based on this, we will know that protein can be, the knots are common. And the question that I would like to explore today with you is how knotted and lasso and leak protein can fold, if the thermal fluctuations are sufficient to make knots in the proteins. So how protein can fold? Not going to the details about the folding of the protein or protein folding with the trivial topology, we assume this is the free energy landscape of proteins, and then you have some random configuration, and then protein can make some small local interaction and can easily find a way in reasonable time to find the minimum of the energy. So we assume that the native contact that exists in the protein in final conformation are sufficient to guide the protein to escape from the local trap to the native state. However, this funnel landscape is not so easy to understand from the point of view of knotted protein, because in this case, you know that not all part of the landscape can be accessible for the protein, because you cannot cut the protein chain and just make a knot. So you have to explore, but only some part of the landscape. So the question that you would like to ask, or I am asking, is how protein can fold and or how protein can make a knot. So you cannot study the protein with the non-trivial topology with all atom molecular dynamic simulation, because it will take you to long time, but you can use some other very simple model that we call them the structure-based model, that they are based on the Lennard-Jones potential that it's mimicking the interaction. So if you will have a question, I am happy to talk about this later on, but I would like to tell you that the result that we found already a long time ago, we found out that protein, it's possible to, that thermal fluctuations are sufficient to fold the protein. However, you do not observe the random knotting. There is kind of the unique pathway that allow protein to make a knot. And this pathway you can see here. So you first have to make a loop, then it's not random loop. The loop is exactly where the knot is located in the minimum of the energy or in the native state. Then you have to make something what you do during your daily life when you tie your shoelaces. You make a slip knot loop. So the slip knot loop, this is what you can see in the middle. It has to be pushed across the knotted loop. So in this case, there was just a twisted loop, but now you have to move the slip knot loop. And when you pull, when you tie your shoelaces too correctly, then you know that you make a knot. So in this case, this is how the protein make a knot. So this is what we call the Rademaisner move. There are now also from the mathematical point of view. So this is telling you that protein can make a knot, but in very unique way. The successful rate, as you can see here, is very low. It's only 2%, but it's kind of the proof of concept that protein, that native contact are sufficient to guide the protein to fold. Probably if you will add some additional interaction, that's the probability is increasing, but still you have to know what type of the interaction protein can use to make a knot. So the message is that knotting of random polymer is different than knotting of protein. So one of the most complicated type of the knots that was found in the protein is a knot with the 6 crossing. It's a 6-1, and it's type of the knot that it's a twist knot. So you can make a twist loop, what you can see here, and then you can twist and twist and twist. And if you twist this 2 times, and then you just, what you have to do is pull one of the termini across the loop. So in this case, you can even fold protein that is quite long, it's above 200 amino acids, in the same way. So you cross this topological barrier just once. So that's one thing to think about the thermal fluctuation and the protein, that if you have such mechanism that you twist, 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 and you cross the topological barrier once, then maybe protein can solve the knotting problem. However, there was some experiment conducted by Sophie Jackson from Cambridge. She was working on similar protein, and she found out that protein can self-tide. However, if you add something what we call the chaperone, so this is some kind of the protein, they can help and speed up this process. And additionally, she made a very nice experiment. She attached two huge proteins or domain to both termini of the protein, and then she found out that still this protein can fold. However, here there's a kind of the problem with the interpretation of the experimental results, that you have to be sure that you really untie the protein, because based on all our knowledge up to now, if you unfold the knotted protein by the huge temperature, by the huge thermal fluctuation, you will unfold the protein, but not will still be embedded inside the chain. So this is very nice experiment, but additional proof that the protein was untied, it will be nice to, it will support this pathway. So this is telling you that protein can knot in cell-free system, so you don't need any additional maybe help to make a knot. So on the right side, you can see the protein that is composed of 3 domains, and the green one, so the middle domain one is knotted. Is the deepest knot ever found now in the proteins. So it's the same something what it was suggested over 5 years ago by Sophie Jackson, but such protein we found recently, or let's say 2 years ago. And now you can ask the similar question: can we fold this protein, and how this protein can fold? So then you can think that maybe you can, because protein is much longer, maybe the random knotting can happen here. So the protein can make a huge loop, and then one of the termini can cross above this loop, and you will make a knot. The other possibility is the pathway that I was suggesting before, that you make a twisted loop in the native position, and then you will drag one of the termini, and then you will make a knot. However, there's also another possibility, that in biology they have something what they call the ribosome. It's you can think about this as a tube which can make the protein chain, and then when the protein chain is pushed across this tube, maybe there can be some special unique conformation, and there will be the force to push the chain across the loop. Because in both these cases, in the random knot, still you need to have something, some external force to push the termini across the loop, and the thermal fluctuation probably are not sufficient. And in the case as well, in this case, when you have such long termini, that probably it's hard to imagine that this mechanism will work. But we tested this based on the very simple theoretical model. So we asked the question: can we make a random knot when we have such long protein? So then you have to make 2 experiments. You can create shallow knots, or you can unfold the protein and have the configuration when you start with the deep knot. And then you can ask the question, if from the shallow knot you can move to the native position, or when you have this deep knot, then you can fold the protein. And what we found out that we never almost observed that if you make a shallow knot, this knot will move along the chain, even with very high temperature, to the native position. So making the shallow knots, it's not sufficient to lead protein to the native knotted conformation. However, if you start with the deep knot, almost in the native position, then you can probably fold the protein. However, there is this problem because you have to jump from this shallow knot to the deep knot, and that's something what we did not observe in any polymer model that we constructed that was similar to the protein. So then you can make another experiment. You can try to fold the protein in this way that you will have the twisted loop and see if there's enough thermal fluctuation to push the termini across the loop. And unfortunately now we rather observe misfolding and never correct folding. You can make another experiment. You can take only this green part that is supposed to be knotted and see if this green part, when you will cut this domain, the blue domain and the red domain, can fold. And that in this case, we find out that if the termini are not too long, the protein can self-tight, and you still observe the slip knot mechanism. So the thermal fluctuation are sufficient here, and we do not observe the random knotting, but we always observe the slip knot mechanism. So you make you decrease the entropic contribution by making the loop that is pushed by thermal fluctuation across the twisted loop. So what about the ribosome? So this is the ribosome. This is the molecular machine that it's putting, that you can say that make the protein chain by putting together the amino acids. And when you attach one amino acid to another one, you have additional force that is pushing this red chain that is already protein outside the ribosome. So you have this additional force that maybe can help you with knotting. So you can you have another example how you can present this ribosome. That's just a tube that has some curve at the end. And in this case, you can build a very simple statistical or physical model. You can construct the tube model with some additional force that is coming from formation of the nesting chain. You can additionally simulate with the van der Waals interaction, van der Waals type of the interaction between the protein and the surface of the ribosome. So we constructed such model, and we asked the question: can protein self-tight on the ribosome? And I hope if the movie will work, yes. So this is our presentation of the model that we constructed. So first we make the loop, or we create the ribosome, and then you can see this is the one of the chain is going outside of the ribosome, and the blue part, the green part, is the part that is supposed to make a knot. And what we observe here is the formation of a twisted loop on the surface of ribosome, and then you can add the interaction between negative charge of the surface, and then let's see what's happened. And then you see that the protein is just pushing the chain across the loop. So with this, we find out that this is one of the possibilities that biology can use to fold the protein. So if you have a stable protein, there is enough force that this protein can dissociate from the surface of the ribosome. So we believe that this is one of the possibility how protein can fold, or when the protein will possess a very deep knot. So additionally, I told you that some protein can make a lasso. So this is when you have the protein chain is closed by the cysteine bridge. So to find if proteins can possess such conformation, so this is a protein, and as you see by visual inspection, it's quite difficult to see if this loop that is closed by the orange beads is crossed by any termini. So what we did, we constructed something what we call the minimal surface. So you know this from SOAP film, and from the mathematics you constructed this by the triangulation method. So we span the minimal surface on a protein, on the protein chain that is close, and then we check if this minimal surface is crossed by termini, and by vector products we know if it's direction of the crossing. So when you apply such very simple technique to all protein structures, then you can find out that in the case of lasso, there's at least 80% of protein that possess this type of the topology. And moreover, you can find that there's a different type of the topology. So you have this something what we call the simple lasso. So one of the protein tail is crossing the loop. However, you can find something that it's quite interesting from also statistical point of view. You have something what we call the supercalling. So this is what you can see on the left side. In this case, the tail is crossing the surface more than one, or in this case, 2 times from the same direction. So this is something quite interesting, and there's an interesting question to ask if the thermal fluctuation are sufficient to make such topology in the time that protein can still fold and have the correct biological function. So we did the same kind of the experiment what we did before. So this is the protein with the supercalling. And then you can see this, we span this minimal surface. Then you can see that it's this minimal surface is crossed 2 times in the same direction. Because the cysteine bridge can be formed in oxidative condition and can be broken in reduced condition. In the cell, we first check if this protein can be folded what is the speed of the folding of this protein and the free energy landscape without the cysteine bridge. So this is what you can see here. This is the number of native contacts. So the contacts that are formed in the native conformation or minimum of the energy when the protein is folded. So you are not expecting to make all the contacts. So this is why you don't have the minimum is not at 1, but it's a thermal equilibrium that it's around 0.9. And there's one barrier that you can see. And you can as well have a different representation of this of root mean square deviation versus number of the native contact. And you can see there is well-formed barrier. But then you can ask additional question, what will happen if you will have non-trivial topology, so when the loop will be closed. So in this case, you can observe that almost majority of the contacts are formed before you make non-trivial topology. However, there is a very nice topological barrier when you have to cross, when you have to make the additional crossing. So the first crossing is not difficult because protein is still unfolded and you can easy cross. But to make the supercalling, you have to cross this barrier again. So we find out that, as you can see here, that it's still possible. So the thermal fluctuations are sufficient to cross this barrier, but there's also a nice observation that in similar way as in knots, when you have to cross the topological barrier, the most efficient way to do it is by the slip knot loop. So this is what you can see here on the right, that you make our first up, you can see a small slip knot loop, and then the slip knot loop is pushed by the thermal fluctuation. So it seems that nature developed some kind of the unique mechanism to cross the topological barrier. But what I think it's even more interesting is that to think what the topology is giving to the protein. And here we find out that maybe you can study the fluctuation of the minimal surface. So this is what you can see in the blue. So blue is a variance of fluctuation of the minimal surface, and the red curve is telling you how many crossings do you have. So in the beginning, you have a lot of fluctuation. So this is time of folding. And in the beginning, you don't have you have very slow number of the native contact, the blue curve, and there's no topology, no crossings. But over the time, you cross first time. So you make one crossing. And then when you make the second crossing, what you can observe here, that this change in the fluctuation of the minimal surface is decreasing. So we believe that based on the fluctuation of minimal surface, we can measure influence of the topology on stability of the protein. So it's on the right side, it's maybe easier to observe this, that there's a small difference between the fluctuation when you have just one crossing and when you make a second crossing, when you make non-trivial topology or the supercoiling. So the fluctuation of the minimal surface is telling you they are decreasing when the additional crossing is formed, and this it's bigger difference than the number of native contact, because the number of native contact is increasing, is the protein is almost folded. So maybe the minimal surface approach or the fluctuation will be method to measure the influence of topology to the protein. I don't know how many minutes I have still.
You have 4 minutes, including questions.
Okay, I have 2 slides, so it's perfect. This is the lasso that we analyzed before to make the to find the minimal surface, to find the lasso. So this is what you can observe how we constructed this, but sometimes you can, the tail of the protein can be longer. And in this case, you can see there will be that you can make a second loop. And when you make a second loop, then you can already observe that we try to find a technique to find links in the protein. So we use this method to scan again all the proteins, and we find out that there's only 2 types of links that can be formed in protein. So that's from the statistical point of view, links are really not things that happen in protein. And why they are important? Because the links, it seems that protein with the link topology can live or conduct the biological function in very high temperature, almost in the boiling temperature. So in the case, in this case, you can make another nice experiment to test if the topology influences the stability of the protein. So you can construct 2 proteins or 1 protein, but with 2 different topology. This one is non-trivial, and on the right side, it's exactly the same number of the cysteine bridges, but trivial topology. And then you can measure what is the probability to unfold the protein. And when you don't have this is the energy barrier to unfold the protein without any cysteine bridge. When you add the cysteine bridge, the blue one loop, this is the energy barrier. When you add when you make the red one, there is no difference really from the statistical point of view, which one the energy barrier will be higher or lower, it's almost the same. However, when you have 2 cysteine bridges, then you can see that this barrier is much higher. So now it's a question, if you have exactly the same protein, exactly the same number of the cysteine bridges, but non-trivial topology, the energy barrier will be lower, the same, or higher. And we find out that the energy barrier is higher. So this is, I think, a very nice way to show that this non-trivial topology is introducing the stability to the protein. This cannot be conducted in the case of knotted protein, because we don't have the protein with exactly the same sequence of the amino acids, the same fold, but it will be unknotted. So to finish, today we know that there is another group of protein with non-trivial topology. We find out protein can form theta curves. So there will be a lot of study of such topology. And if you would like to know if protein is knotted, possess lasso links, then I encourage you to use one of this server. And with this, I would like to finish and thank you for your attention.
Let's thank the speaker. Well, I think we're out of time unless the main organizers say that there is time for one question. Okay. Actually, I also have a question, but I will put it in a mail to you. So,
okay,
Joanna, you hear me? Yeah, I'll put it to you in a mail later. Yeah, it was a great talk.
Thank you.
Here comes a question.
Thank you. I wish to ask you, what about entropy? So you can describe the different structure or the dynamics through and from entropic point of view, and if there are any entropic barrier, if the polymer change from one structure to the other one.
Mm-hmm. So it's a very good question, but I don't have easy answer for this. So we believe that we can use more statistical point of view approach to show that the entropy is decreasing when you make the slip knot conformation. So the slip knot is this is the unique way to make, on one hand, a stable hairpin that it's not fluctuating too much. But when you make at least one native contact, it will be sufficient to move this loop on the other side of the twisted loop. So the entropy is decreasing when you make the slip knot loop. And if you make the test that you make you would like to push the chain in a straight conformation, it will just be stuck in the loop, but there will be no efficient force to move it on the other side.
Okay, we thank you for this explanation and answer, and we thank you again.
Thank you.
Are there any announcements from the organizers? I think there are. Yeah.